So good morning. My name is David McNeil. I'm here to talk about closure macros, and specifically looking into the observation that many have made that macros are hard. So I did some research preparing for this presentation here, and kind of my first result is that macros are actually really scary. And this is based on my finding of the feeling that I feel when I look at other people's macros. So that's kind of the OPM problem. Kind of my second finding that I came up with was that macros are actually a whole lot of fun. And this comes from my feeling when I'm spewing out a pile of macros and expressing my creativity and having lots of fun doing that. So it's a matter of perspective sometimes of whether they're scary or fun. But I found if you follow the macro path long enough, eventually you'll find yourself in a really hard place. And so if you're like me, you'll call another one of our coworkers over, who's a fellow named Nate Young, and he knows like Haskell and Common Lisp, and he knows Clojure really well. So he'll come over, and he'll kind of hold up a mirror to me to let me see kind of what I've been doing. And he basically says, yeah, he's too nice to say it like that, but effectively he's communicating to me that, yeah, there's something you're doing that's not quite right. And so after that happened enough times, I kind of started to think about it and tried to understand what's the difference between how I approach Clojure macros and how he's approaching it. And what came out of that is I realized that I had a very primitive view of how macros and Clojure worked. So I had this idea that there was simple, basic Clojure, and then there's kind of big, complicated macros with a lot of action, but I could kind of make them work, just kind of cookie cutter, do some things. And I realized that Nate actually had a significantly different model. He had a significantly different model in his head, as near as I could tell, about how macros worked. As far as I could tell, what he had is he had a set of discrete components, kind of features in Clojure, that he understood in isolation. And then finally, when it came time to put this capstone on of macros, he was now able to apply what he knew about all those underlying pieces and kind of just do some extra magic on top of it. So as I thought about this, I realized that one of the truths underneath the statement that macros are hard is the observation that macros are demanding. So one of the reasons that they're hard is because they have a way of showing flaws in our thinking, like limits of our understanding about how Clojure actually works. So this was kind of a breakthrough for me because now I could take on these topics and I could dig into them and understand them better and thus try to improve my ability with dealing with macros. But they're not just hard because they demand an understanding of these topics. They're also hard because they demand that you be able to think clearly and accurately when there's a lot of action going on in your code. So Clojure is really powerful, and you can make compact forms. But if you really study what those forms do, there can be a lot going on in terms of what the reader does, what macro expansion does, different things being evaluated. So macros are demanding because you have to know a lot, but they're also demanding because you have to think well and think carefully about your code. So with that kind of basis of understanding what I wanted to go after, I started to think about programming models and how I thought of how Clojure worked. So that's a big theme of what I'm going to do in this talk is I'm going to build up an ever-increasingly complex model of how Clojure actually works. And that's a key for me in understanding how to use macros. So you could start out with a pretty simplistic model, and you could actually get pretty far. I mean, Clojure is pretty powerful and intuitive. You could kind of just get in, write some code, evaluate it, and get some results. But of course, we know it's more complicated than that. So first I'll talk about here the REPL model. So you have Clojure text, Clojure code represented as text. The reader reads that in. It becomes Clojure data. And now you evaluate that. So it takes a Clojure object in, it gets evaluated, produces a new Clojure object. And then finally, you can print that out. So this is starting to build up a more mature understanding of how Clojure works. And macros push that a little bit further. Because with macros, you actually have to understand what the reader's really producing, because the macros live in this land of the values that are produced by the reader. So since macros live there, they force us to understand the reader in deeper ways than we would normally if we're just writing like non-macro code. So that's really the starting point, is to understand Clojure well, or understand macros well, you have to go back to basics and really make sure that you understand how the Clojure reader works. And the first definitive place to go look for information on the reader is the Clojure website, the reader page. So that'll give you a good feel for all the basic forms that are out there. And basically, at its heart, what the Clojure reader does is it takes in a series of characters, which represent Clojure code, and converts that into Clojure data. So the way I think of it is that Clojure code, when you look at a text file with a bunch of code in it, it's really just serialized Clojure data. And so the reader is just the implementation of that serialization format. So if you look through all your def-ins and everything, it's just lists and vectors and maps. It's just Clojure data that has a particular serialization format in text that's human readable. So the reader implements that serialization protocol or whatever, and you can learn about that, you can read about that, but really you end up needing to experiment with it. So I'm going to show a bunch of code here where I experiment with the Clojure reader, and it's all in 1.3 except where I note otherwise. So if you're going to experiment with the reader, you might be tempted to just start typing at the REPL. I think that's a really bad idea because at the REPL, it's doing reading, macro expansion, evaluation. It's all in one fell swoop there. And what we really need to do to understand the reader is we need to tease apart and just call the reader. So I'd recommend doing a little test function, something like this. This uses the read string function from Clojure core, where you just pass in a string of Clojure code, and it will return whatever would be read or whatever is read from that by the reader. So with this test function, we pass in a string essentially and get back the string. We get back whatever is read in. And then to really understand what the reader's doing, you need to see the type of that object. Because often objects will print out, but they don't print out in a really distinguishable form. They print out in an ambiguous way where you don't really know what type of object it is. So we really want to see what class the object is when it comes out. So you can go do this on your own. Just start experimenting with all the various forms. I'll quickly go through some of them. I won't talk about all these. You've got the numeric forms. You've got various miscellaneous literal forms coming in. This one's slightly more interesting. This is a Java object literal syntax. I think this was introduced in 1.3. So what you can do is you can put a hash, a class name, and then a vector of arguments, of objects that will be passed into the constructor of that class. So this gives you a way in coming from the reader to directly instantiate an object. So the reader will read in and produce the object for you. You don't get like a form that would produce the object out of the reader. You get the object itself. This is used with records. There's no intermediate size there, is there? You can also use this alternate syntax for records where it's really name-value pairs. So instead of a map, or instead of a vector, you can pass in a map and construct record objects that way. This is a bit of 1.4 syntax. So in 1.4, they're, I guess, experimenting with an instant in time literal. So you can put hash inst and then a string, which is an ISO date time string. And by default, that will read in as a Java util date, and dates will render in that syntax by default. The kind of interesting thing about this is it's starting to move towards a user configurable reader. So the idea is that you can plug in at runtime your own module which knows how to handle instant literals. So you can produce whatever kind of object you want out of that. So if you want to produce like a JOTA date time, you could do that. So it's moving towards like a controlled manner of letting users control what the reader does. So as far as I know, this is experimental, but that looked like the current state of it when I looked at 1.4. Then, of course, you've got the basic collections. So that's not too interesting. You've got various dispatch forms. So if you see a form that starts with a hash, that's typically doing some kind of reader magic. And so if you hear people tell you that Clojure syntax is easy because all there is parens, that's just bunk, right? I mean, if you look at this, there's a lot of syntax there to learn. And if you're going to do macros well, that's the foundation you need, is to understand what the reader's producing, because that's what's... Yeah. Some of it's going off string. Sorry about that. Some of it's not too important. Yeah. So here's a little bit more interesting one. These are all conses, actually, so you can see what those produce. But here, this is the syntax quote. And this one's kind of a bit surprising if you're not expecting it. So like, take that second line. You've got a backtick and then the vector with 1 and 2. Just a few characters. Well, by the time that gets read in, that actually gets read in as this whole pile of code to reproduce that collection. So this is why it's important to understand what the reader does, because a lot of times what comes out of the reader looks dramatically different than what goes into the reader. And this one, syntax quote, is really quite important for macros because it's the core of how you end up producing code in macros. And so really what's important to understand about syntax quote is as soon as it gets read in, it really just gets read in as a big pile of code. So when you see a syntax quote, you might end up erroneously thinking, oh, that's making like a syntax quote object, and that object's being passed around. That's not true at all. You can think that for a while, and it sort of works for a while to think that way, but it's not what's actually happening. So anytime you see a syntax quote, as soon as it gets read in, that syntax quote is gone, and you've just got a pile of code there to reproduce whatever collection you passed into it. So for instance, if you pass in this form, you get this big pile of code out. But as soon as you read it, the syntax quote is gone. So the mantra I have for that is there actually is no syntax quote. Just get that out of your mind. If you're talking about making a macro and you're like going to produce a syntax quote out of it, that doesn't exist. You can't do that. So that's the core of the reader. The evaluator, or how evaluation works, is the next key piece I'll look at. Again, the definitive reference point is the Clojure website. Basically what the reader does, or I'm sorry, the evaluator does, is it takes in a Clojure object, performs evaluation on it, and gives you a new Clojure object. And the trick is that evaluation, the rules on how it evaluates are specific to what type of object it is. So I'll look at a few of those. The most interesting one, of course, is lists. So if you evaluate a list, what the evaluator does is it looks at the first item in the list. If that resolves to a function, then it will evaluate all the other items in the list and pass those in as arguments to that function. And this sounds really basic, maybe this is elementary, but it's important to really get fixed in your mind what's going on, because when those parents start flying and you get a lot of confusion, you have to really be able to think slowly and clearly about exactly what's happening. So each of the arguments will be evaluated, they'll be passed into the function, the crank is turned on the function, a final answer pops out, and that's the result, that's the final value that comes out of evaluating that list. So now I'll contrast that with how macros are evaluated. It's very similar. There's this core body, which will do some operations on the inputs to produce an output, but the evaluation rules around it are quite different. So here, when the evaluator sees a list, if it looks at the first item and that's a macro, then what it will do is it'll pass in the remaining arguments, the remaining items in that list, as arguments to the macro body, however they came out of the reader. So that's why it's so important to understand the reader, because whatever the reader produces for each of those items, each of those expressions, that's what will be passed into the macro. The macro will do whatever it does, have its implementation. It'll produce a value, and now the value that it produces will be evaluated. So typically the macro is producing code, which is then run. And that's the main way to understand macros, at least for me, is a macro is a way of transforming the code, like before it's evaluated or as it's evaluated, depending on how you think of it. So here, this is kind of a stylized view of what if-let could do. The real implementation isn't this crisp and clean, but you have this if-let call, which is code. Now the macro, the if-let macro, has a chance to transform that code before it gets run, and that's what macros are all about. And this lack of evaluation of the arguments is one of the keys to the syntactic power of macros. So since the arguments are not evaluated, that means the arguments can be something that would not evaluate. So for instance, in this if-let, this x out here, that wouldn't evaluate. It would say, if that was a function call, it would say, hey, there's no x, you can't do that. So that's the syntactic power of macros, is they can take forms which wouldn't evaluate, and they can transform them into a form that does evaluate. And that's what lets you really kind of extend the syntax of language, of Clojure, to add in your own like DSLs. So looking at them side by side then, functions and macros are similar. They both have a body of code that's run with arguments and produce a value, but the evaluation rules around them are different. So really for me it distills down to these three main differences of how macros compare to functions. Macros have these special evaluation rules, like I've been talking about. I'll talk about this a bit later, but macros actually, the body of macros run when their calling code is compiled. And then finally, macros are not objects. So this is one way, sort of a primitive way to understand why you can't use macros in higher order functions. So what I mean by macros are not objects is if you look at functions, if you do a def-in of f, and then you reference f, Clojure knows what you're talking about. You can get an object, which is the function. If you do that same thing with macros, you're out of luck. You can't do that. You def a macro with m, you ask Clojure for m, it doesn't know what you're talking about. So because of that, that's one way to understand why you can't pass like the macro name into a map function, for instance. So then I would recommend doing experimentation just like you do with the reader, but do that similar kind of thing with the evaluator. So here I have a function where you pass in a string, you read that string in to see how it reads, and then just call eval on whatever that produces. So this is a way, using read string and eval, you can call directly into Clojure and start experimenting to see how the evaluator works and how the reader works. So these aren't very interesting. Symbols, of course, when they're evaluated, they try to resolve to whatever the value of the variable is. Keywords are very similar to symbols, except they eval to themselves. It's kind of interesting to see. If you just have any old Java object and ask the Clojure evaluator to evaluate it, it will evaluate to itself. So you can evaluate a date and get the same date back. Lists, of course, we talked about. If you have other collections besides lists, the way that they evaluate is they'll produce a new collection of the same type, but with all their contents evaluated. And again, you've got this kind of abundance of forms that if you really want to make a study of it, you kind of go through them systematically and understand how they all work. But I'm going to leave that and start talking now about quoting, because quoting does turn out to be a key piece that we use inside of macros, but it can be really understood as a standalone piece before you ever introduce macros themselves. So the way I understand quoting, the way I think of it is it's very much like quoting in the human language. So if I have this sentence, and there's this phrase in there that says launch the missile, right? You can think of that as data in the sentence. It's not a command. You're not being told to do that. It's something that's going to be discussed as a phrase. In the same way, when you see a quote in Clojure, it's the same idea. So this plus 1020, we're not instructing the computer, hey, right now, go add these numbers. But rather, we're going to talk about this list, plus 1020, as a piece of data. So you can put into the reader a quoted form, and then when you eval it, it will just produce that quoted form. Like, it'll produce whatever was inside of it. So I think of it as quoting as like an anti-eval. So if you've got a form, you put a quote in front of it. When the eval comes in, the eval kind of annihilates the quote, and you're left with the form. That analogy holds up if you put 3 quotes in front of it and hit it with 3 evals. Right? One by one, they'll eat through the evals until finally you get to the form. And if you eval that one more time, it'll now run the code that's inside of it. So quoting is just kind of wrapping up a form to protect it against eval. So that's quoting. That's just like the normal tick. Syntax quoting uses the backtick, and it's a different beast. Kind of at its core feature is similar to quoting, right? But it has some additional features that turn out to be useful for writing macros, but can be understood outside of macros. So I think it's worth studying them outside of macros. So the first difference I'll talk about here is quoting and syntax quoting handle symbols differently. So if you quote a symbol and read that in and eval it, you'll just get whatever symbol you put in. But the way syntax quote works is as the syntax quote is being read in, any symbols that it finds, it will resolve in your current namespace and namespace qualify them. So it's not at all obvious when you first approach it, like why this is happening or that this is happening, but that's kind of an underlying feature of syntax quote. And this also explains the idiom, if you've seen it, where you have syntax quote, and then if you want to put in a bare symbol, you'll put tilde, tick, symbol. So this is why that works, right? Because we're backticking, then we unquote, and then we quote again, but we quote again with regular quote, not with syntax quote. Because normally you would think, well, you quote, unquote, quote, it's all redundant. but you're unquoting and then quoting back into the regular form, which doesn't namespace qualify symbols. Another way that syntax quoting handles symbols differently is you can append a hash to the end of a symbol, and when that syntax quote is read in, so again, this is a reader time feature, it will expand all instances of that symbol with the hash to be a generated symbol. And this, of course, is used to avoid collision between the expanded code and the overall context that that code is going to be expanded into. And we saw hints of this earlier, but syntax quoting handles collections differently than quoting. So here I've got an example where I quote a map and I syntax quote the map. You can see they produce radically different things, right? The quote just takes the collection as a literal and just carries that through, whereas the syntax quote will produce this pile of code to reproduce whatever collection you gave it from its constituent parts. And again, as soon as this gets read in, syntax quote is gone. It's just a pile of code at that point. So the fact that syntax quote expands out to this pile of code means that we can now have this feature where we can have holes in our template where we can plug in code. So the way that's done is with unquote. So this is showing two examples. You can either have this third element in the list be plus 100, 200, and it just comes through as a list. Or if you unquote it, then what you get is the result of evaluating that expression. So to look at how that actually works in terms of the code that gets read in, or the form that gets read in, if you read in that first form without the unquote, you can see down here it'll just construct a list with the plus and the 100 and the 200. It won't run that code. It'll just construct a list like that. But as soon as you unquote it, you get this different form. It'll just put that form into the place in the overall pile of code. So what this has the result of doing is now when you eval this whole, when you execute the code that comes out of this, it'll build that list, and at the time it's building that list, it will run that expression and put the result of that into the overall list. So there's a splicing unquote that will take a sequence and kind of lift it up into its surrounding sequence. So just kind of for completeness, that's something else you can do with syntax quote. So the next piece I'll look at is a little bit more about the evaluation process, and not just the simple evaluation rules, but kind of how it ends up working out in practice. So here's a pretty simple macro. It takes in a sequence. It'll find the first item in that sequence and print it out. If you call it on 1, 2, 3, it prints out 1. Now it's important to note here that the first and the print call are happening like at the time the macro expansion happens. So they're just in the body of the macro. So the macro's not producing code to do that. It's actually doing that when you call the macro. So here's kind of the first test question I have for you. What will this print? Anybody care to hazard an answer? So you might think it would print A. I heard mumblings. Somebody's? A nil. So it's going to print the first item in the list. So the question is, what's the first item in the list? It's not at all obvious. You'd have to really think it through carefully. What it's actually going to print out is closure core seek. So how in the heck did this happen? So the thing to remember is macros are handed whatever the reader reads in. Well, the reader in this case will read in for this first argument to first M. It'll hit that back quote A list. It reads that in as this pile of code, a pile of code to recreate that list. And it just so happens that the root of that list, or the first thing in that list, is closure core seek. So you get out closure core seek. And this is kind of getting at the heart of why macros are hard, because you really have to switch your way of thinking, and you got to think about an expression in kind of two ways. It has its reader expanded form, and then its actual evaluation form. You got to force yourself to think about how does this get read in. So this pile of code for the syntax quoted A, that would produce a list with A in it, but it hasn't actually been run yet at the time the macro is called. So what if we slapped in an eval call? Anyone want to guess about what we get printed out now? Could guess print A. So what's the first argument to the function here, or to the macro call? The argument is, what's the data type of the argument? It's a list. So when the reader reads that list, what will be the first thing in that list? It'll be the symbol eval. So what you get out is eval, right? So it's not going to be evaluated yet. The macro just gets whatever gets read in. And that's the point I'm trying to hammer home. All right, so I've been talking about this macro expansion time. So you kind of have these two places where code is run with a macro. The macro body itself runs, produces some new code. That code is then evaluated. So you've got the macro expansion time, and then you've got this other thing, which is like the macro result evaluation time. And that's not what these are typically called. Typically, these are called compile time and runtime. And compile time could be macro expansion time as well. These names are too simplistic in a way because there's actually more happening than these indicate. But they kind of make sense, and they're used pretty widely. So they make sense if you think of a Clojure source file, and you're going to load in that source file. When you load that in, all the def-ins in there will all be compiled. So when those def-ins are compiled, the macros run. So you talk about the macros running at compile time in that sense. And then later, after those def-ins are loaded, something will call those def-ins, and now the def-in will run, and now the code that was expanded from the macro runs. So that's kind of where that comes from. And if you read different books and tutorials on it, they'll often talk about compile time and runtime, and that's the distinction that they're talking about. So this then is very similar to the example I had a moment ago, except now instead of the macro body doing that first, what this will produce is code which will compute the first item in the sequence and return that. So now we're moving. The first example I had was happening at macro expansion time. This is happening at that later runtime, or when the result of the macro is being executed. So of course, for 1, 2, 3, it prints 1. And I have to ask, what does this produce now? And for such a small, trivial example, it's actually quite tricky. Unless you just have good intuition, it's quite tricky to think through in detail exactly what this will produce. It does actually produce the A now, but if you really want to think through the path that it got to, that it went through to get to that, it's pretty complicated. So you got the backtick A, which makes this pile of code to produce that list with the A in it. That whole pile of code gets passed in, and now the macro is going to make a new big pile of code, which is pile of code to make a list with first in it as the first item, and then that pile of code as the second item. So that code actually gets run as part of the macro body, so it produces that list with first as the first thing in it, and that pile of code to produce the list with A as the second thing in it. And now that gets evaluated. It sees that first is the first item in it is first. That's a function, so it'll evaluate the second thing, which turns it into a list, and now first takes the first item of that, which is an A. So it's really, there's a lot going on for just a really small bit of code. And a lot of times, like I say, you can have intuition and just kind of go with the flow, and it works. But you inevitably end up in that spot where your intuition is off. Your mental model of what it's doing doesn't match reality, and you've got to be able to slow down and just really take it piece by piece to understand what's happening. So here's a similar kind of puzzle. Say we have a set of nested function calls here. So each time you call myFn, it'll print out the first argument, which is just a number, 1, 2, or 3, and then it'll return and pass up the stack the second argument. So what order will these numbers come out in? Anybody? Anybody? 3, 2, 1. That's not too surprising, right? I mean, that's kind of how we're used to Clojure working. Right? It's kind of like this bottom-up feel of evaluation. But here the follow-up question to that is, which one of these evaluations was actually started first? And the answer is, when you go to evaluate this form, the evaluation, it starts at the top. All it has is the top-level form at that point. So it actually starts the evaluation of myFn1 first, and it's in the name of doing that evaluation that it then evaluates its argument, which is myFn2, and then its argument is myFn3. So, right, it's just like you'd expect. You have these nested calls. So you roll down into myFn3, and then you roll back out. So myFn1, the evaluation starts first, but since they're nested, myFn3 finishes first. And that's markedly different than the way macros work. So this is a very similar example. It was print out the number and carry the second value. What order will the numbers come out in now? Anybody? One, two, three. So the way macro expansion works is when the macro is invoked, the arguments are not evaluated. So it just walks through it, does the first macro, carries through whatever form is passed as the second argument, and walks all the way down. And then the same question, which one was started first? And of course, my macro 1 was started first here. So this is really a different dynamic than you get with nested functions, where nested functions, it really was nested calls, and you kind of walk it down the stack. Here, macro evaluation, and this was kind of surprising to me, is it ends up being, it's sequential, right? It starts expanding macro, the first call, and it finishes that before it even starts the second one. So you end up with this sequence of operations. And again, as things get complicated, you've got to be able to think through in your mind, okay, what exactly is happening? So this is a bit more exotic case. We've got a mixture here of macros nested with functions. Anybody? I heard a 1, 3, 4, 2. Anything else? So of course that's right. So the way I think of it is as you walk down the stack, the macros get called as you go down, and then as you come back up, you can think of the functions being evaluated. So I'll move on now to an example of let. So say we wanted to write our own let macro. First off, why does it have to be a macro? Because the arguments, they won't evaluate if it's not a macro. If we want to use this syntax, it has to be a macro. So the main thing let does is it establishes this binding between symbols and values. So if we can't use let, we're left to try to cast about and find how else can we bind symbols to values. It turns out that's one of the main things functions do. So if we defined a function here, it took the symbols x, y as parameter names, and when you invoke it, you can then define a value. So the function call will then bind those values to those variables. So this then is the basic recipe for how you write macros. And it's not a recipe like, oh, let's blindly follow this, we don't know what we're doing. It's a recipe like, this is really tricky, we know what we're doing, but if we follow a recipe, we'll have a nice systematic way of getting the answer, because it's actually quite challenging. So the recipe is you take a sample invocation. So here we want to call my let, and we want to call it like this. And then you have to write out, this is the code we would like this to produce. So we have a sample invocation, and we have prototype output. So this is like the input and the output to this macro black box. And then you can kind of mechanistically start turning the crank here. You take the expected output, you make that be a code template here, make it be a syntax quote, and then look through it for anything that actually needs to be parameterized, and you replace those occurrences with unquotes. So you replace them with, make holes in your template to fill in values. The next thing you can do is, as you're building up that form, you've got the syntax quoted form, you need to wrap it in a def macro call. And you can go back to your the invocation, the sample invocation, to figure out, okay, this is the name of the macro, and plug that in. You can look at the sample invocation to see how many parameters there are, and you can understand what they mean and give them names. So now we've built up a def macro form. And then the final part is to tie those holes to the values, to the parameters that we have coming in. So, of course, if we take the even numbered items from that vector coming in, that'll be the names, the symbol names to use in the function parameters. If we take the odd numbered items, those will be the values. So that's the rest of the bindings. That's take nth 2 of the rest of the bindings. And then the body is whatever expressions they put into the body, we'll put those as the body of the function. So we can call that, and that works. You can use the built-in macro expand 1 function, which will just do one level of macro expansion on whatever form you give it. And you can see that, yes, it actually does produce what we were setting out to produce. Let's skip that. So I think just sort of as my professional obligation, if I'm talking about macros, I have to have some disclaimers in there. I'm not advocating just rampant use of macros. So when do you actually use macros? And the way I've kind of distilled my thinking down on this is if I'm making a library for a person who's going to sit there and type the characters to talk to it, then I would consider using macros to try to achieve some kind of syntactic clarity or some nice syntactic sugar for that. Or, of course, if I want to do some pile of work at compile time, I don't want to do that every time at runtime. But that's really rarely seen in what I do, so it's mainly often about just the syntactic sugar. So if it's going to be a person typing the code, or even maybe just a person reading the code, and I want it to look really nice, consider macros. But other times, and this seems like most of the time, we're making libraries that are going to be used by applications above us. And in that case, it seems clear to me you should absolutely prefer macros. Macros, they don't have to worry about quoting things. All you have to do is quote the stuff going into a function call, and its evaluation rules are very similar to macros. Applications don't care about that. They get data in, they pass it to your library, it's okay. And compile time expansion just, in most cases, I don't think is useful, especially if it's a dynamic application using your library, so it's dynamically building up structures to call your code. And it really, this addresses issues. If you make your library as macros, it makes it hard to use in many ways because macros don't compose well with functions. So the way I think of it is when you have a macro, you're really entwining two separate ideas. You have the body of the macro, which is some kind of transformation on code, but you're locking that body up inside of a macro where you've predefined how it's going to be called and what the calling semantics and the evaluation semantics are. And so this is why, in my opinion, why you see the common pattern where instead of locking that code up in a macro, you actually write a function, a helper function to go with it. So you pull the guts of the macro out into a function and have the macro delegate to the function, and it can do whatever quoting is necessary when it calls the function. And this now gives you two entry points. So you kind of have the functional entry point if you want to do higher order functions with that, and you also have the macro version if a person is going to be sitting there typing the code. So I've kind of pushed on this idea, and I'm toying around with an alternate implementation of the def macro, which will define the core macro just like it normally would, but then also just define a couple of helper functions for you. One is it'll take whatever symbol you give it as the name, and it'll add either a minus or a plus to the end. The minus version is just a function which does the transformation, and the plus version is just a function that does the transformation and evals the results. You can also kind of view this as this is a cookie cutter pattern for how you convert a macro into a function. You basically take the body of the macro, put it in a function, put an eval in front of it, and then when you call the macro, put quotes in front of the arguments, and you've effectively transformed your macro into a function. So if you do that, you can call these, and now you can do things like if I define this macro blah, I can now call map and use the function behind that macro. And it's really not doing anything that we don't do already anyway. We oftentimes, like I say, put these helper functions behind macros anyway. It just sort of makes it more systematic how to do that and makes the syntax for doing that a little bit nicer. So here's another example. This will just take in a sequence and produce code which will calculate the sum of that sequence. So I call it on 0 through 3, I get 6. Called on 0 through whatever 3,000, I get 5 million. So what would you expect to happen if I now call it and just give it one more number, right? It could do 3,000 numbers. Surely it can do one more. Yeah, so we kind of recover from that a bit. We don't have a model right now that can explain why this is happening. Like our model of how evaluation works, there's no place in that for a class format error when you call a macro with one more argument in it. So we're going to have to beef up our model. And something we haven't talked about yet is compilation. So this is a more accurate model of what actually happens when you eval code. And the basic guideline is no code in Clojure gets run without being bytecode compiled. So after the macro expansion, you end up with this pile of code. That pile of code will be compiled into bytecode. And that bytecode is then executed to produce the final result. So the way it would work if you had a file with two functions in it, one that called the other. The first function would be bytecode compiled. The second one would be bytecode compiled. And in that bytecode would be a call to the first one. Of course, that's for functions. Macros are more complicated. So macros here, we really have this two-level thing happening. Macros are Clojure code. So those need to be compiled first. So what happens at macro expansion time is you're actually calling into the bytecode that was compiled from the macro to produce the new data, which is bytecode compiled. So say we're loading up a file that has a macro and then a function call, or a function that calls that macro. You can kind of sort through that when the function gets compiled, it's going to call the code behind the macro, get a result, and then that result will be compiled into the F1 definition. So this is really kind of a radically different thing that's happening here if you compare how function calls get compiled to how macro calls get compiled. And you might say, well, we don't care about this level of detail, but we've got this error, right? We've got this error looking us right in the face. We have to know how to address this. So what's happening is the macro call is producing this big form. That form is being compiled into a Java class, into a Java method. Well, it turns out there's a 64K size limit on Java methods. So once I hit 3281, I'm over the 64K, it can't compile it anymore. So if you're doing a lot of work with macros, you may end up hitting this. Some might say you're doing it wrong at this point if you hit this. But we've done things like we've built parsers that rely on macros, and we kind of weren't expecting to hit a limitation like this. So how do you address it? The basic approach is you need to make the macro produce smaller code. This is kind of a trivial case, so I can do the summing here. I can do that work at compile time. So by doing it at compile time, I can make a new version of that macro that just produces a scalar value. So now I can call that with arbitrarily large vectors, and it's not going to break. So you need to generalize that to your own problems then to say, if you hit this problem, it's about kind of decomposing the work so you can do it in parts, or doing more work at compile time. So here's my last example. This is an internationalization example. If I pass in a string, I want this macro to give me a vector, which has a locale in it, and a string. So you'd like to think, hey, this would just produce, right? That's what you'd like to think it would produce. Actually, what you get is this. So again, we're kind of back in the case where we don't have a model right now of how this could even be happening. So we have to go splunking a little bit and figure out, first off, you can figure out what print dupe even is. What print dupe is it's an alternate way of printing where it'll print an object in the form of closure code, which when read in and evaluated will reproduce that object. So you can kind of think of it as a way of serializing an object out to closure code. But again, we don't have a model that takes into account why this would even be called at this point when we're trying to call this macro. So we have to go back to our model, and we've got to beef it up yet again. So closure data, we said that closure data that's produced by the macro expansion, that will be compiled into bytecode. But closure data is really a superset of Java data. So we can have arbitrary Java objects in that. And when we go to compile those, the closure compiler doesn't know how to compile an arbitrary Java object into bytecode. So print dupe, you can think of it as it's kind of like this backdoor into the closure compiler. You can define a print dupe multi-method on any Java object you want. And if the closure compiler comes across that kind of object, it will go ahead and use your print dupe method to produce text, which is then read, which is then compiled into bytecode to represent your object in the underlying bytecode. So I hope you can see the model you need in your head to understand macros is quite a bit more complicated than what you might have seen before. And I don't think it's gratuitous. I think it's necessary because you hit errors that you cannot explain without having a kind of a high-fidelity model of how the closure evaluation works. And if you keep pushing on this, you can push like even deeper and get a higher fidelity model of how closure evaluation works. And that would look something like this. So yeah, Rich is really smart. So in summary then, based on my research, are macros hard? Yep, actually they turn out to be hard. Not just hard, but they really are demanding. They will find places that you do not understand about closure, and they will bang your head against the screen trying to make them work. But are they worth it? I would say absolutely they're worth it. And the reason is because what they're doing for us is they're showing that we have an incomplete understanding about how closure works. And so I've got to bet on us having a better understanding of how our tools work and actually knowing more what we're doing, we're going to get better results. So that's it. I think I'm out of time for questions, but feel free to hit me afterwards if you have any. Thank you.